I should be live, and I am live. Yep, stream number 19. So let's begin. Today we have to, well, like always in this stream, we are learning Arch assembly, and today we will read about multiplication. Yesterday we did subtraction by addition. If you want to subtract one number from another, then first you have to find its complement of the number which you want to subtract, and add that complement to the number from which you want to subtract, and the result you get will be their subtracted result. And now binary multiplication. Okay. Many processors have hardware multiply instructions. However, hardware multipliers require a large number of transistors and consume significant power. Processors designed for extremely low power consumption or very small in size usually do not implement a multiply instruction, or only provide multiply instructions that are limited to a small number of bits. On these systems, the programmer must implement multiplication using basic data processing instructions. Even when a hardware multiplier is available, there are some techniques available which may achieve higher performance. Okay, multiplication by a power of 2, you can just shift them that many times. If a multiplier is power of 2, then multiplication can be accomplished with a shift to the left. Consider the 4-bit number x3 multiplied by 2 power 3 plus x3 multiplied by 2 power 1 x1 multiplied by 2 power 1. Okay, this is x, and x3, x2, x1, and x0 are zeros and ones at these places, where xn denotes bit n of x. Yes. If x is shifted to left by 1, introducing a 0 into the least significant bit, then it becomes x3, 2 power 4, 2 power 3, this, and this. Therefore, 2 multiply by the whole thing. Yeah. Therefore, a shift of 1 bit to the left is equivalent to multiplication by 2. This argument can be extended to prove that a shift left by n bits is equivalent to multiplication by 2 power n. That makes sense. Now, multiplication of two variables. Most techniques for binary multiplication involve computing a set of partial products and then summing the partial products together. This process is similar to the method taught to primary school children for conducting long multiplication on base 10 integers, but has been modified here for application to binary. The method typically taught in school for multiplying decimal numbers is based on calculating partial products, shifting them to the left, and then adding them together. The method typically taught in school for multiplying decimal numbers is based on calculating partial products, shifting them to the left, and then adding them together. The most difficult part is to obtain the partial products, as that involves multiplying a long number by one base 10 digit. The following example shows how the particular products are formed. Multiplying this by this, I multiply this by this, added this here, okay, this into this, and then 1 2 3 into 5 shifted one position to the left, and 1 2 3 into 4 shifted two positions to the left, and then add the partial products. The first partial product can be written as 1 2 3 into 6 into 10 to the power 0. The second can be written as 1 2 3 into 5 into 10 to the power 0, and the third can be written as 1 2 3 into 4 into 10 to the power 10 square. In practice, we usually leave out trailing zeros. The procedure is the same in binary, but is simpler because the partial product involves multiplying a long number of single base two digit by single base two digit. Since the multiplier is always either zero, since the multiplier is always either 0 or 1, the partial product is very easy to compute. The product of multiplying any binary number x by a single binary digit is always either 0 or x itself. Therefore, the multiplication of two binary numbers comes down to shifting the multiplicand left appropriately for each non-zero bit in the multiplier and then adding the shifted numbers together. Let's suppose we wish to multiply two 4-bit numbers, this and this. Okay, we have this here, we have this here. For multiplying by 0, we get 0. Multiplying by 1, the number itself, by 0, we get 0. Multiplying by 1, get the number itself. First place, 0 shift. Second place, shifted left by 1 position. Third place, shifted left by 2. And fourth place is shifted left by 3 positions. Then we add them all. Notice in the previous example that each partial sum is either 0 or x shifted by amount. Yeah, that makes sense. It is either 0 or x shifted by some amount. A slightly quicker way to perform multiplication is to leave out any partial sum, which is 0. Example 14 shows the result of multiplying 101 by 89 in decimal and binary using this shorter method. For implementing in hardware and software, it is easier to accumulate the partial products by adding each to the running sum rather than building a circuit to add multiple binary numbers at once. That makes sense. We can add them one by one, keep a sum, and then keep adding the next one. This results in an algorithm with O power n, big O of n complexity, where n is the number of bits in this number, the second number. N is the number of bits in the multiplier, this multiplier, and this is called multiplicand, I suppose. There are multiplication algorithms that give even better performance, and some processors use combinatorial multiplication circuits, which are very fast but require a large number of transistors and consume a great deal of power. Okay, there are multiplication algorithms which give better performance, are very fast but use a large number of transistors and thus consume a great deal of power. And they use combinatorial multiplication. Combinatorial as opposed to mm, sequential. Combinatorial multiplication happens all at once instead of this having a loop structure where we get one thing, then we add to the next, and then we add something else, and then we add something else. This is sequential. Here we have things happening one after another. There is a sequence to this, but combinatorial multiplication happens at the same time. You get two numbers, and at the other side, you get the answer without any procedure or anything. So we have algorithm one, algorithm for binary multiplication. Okay, we have an accumulator circuit which has 0. Then while y is not equal to 0, do this. If LSBy equal 1, LSB of y is equal to 1, then add x, okay, and then end if, and then after that, after everything, after this, after adding x to y, shift x by 1 bit, shift x left by 1 bit, so that the next time I will be adding, I will be adding to a shifted, I will be adding a shifted value of x, and shift right y 1 bit to get uh, the next LSB. That makes sense. Equivalent multiplication in binary and decimal. Binary we have this, in decimal we have this, and in binary we have this. And this is long as, and we are not uh, writing down the places for zeros. We are just skipping them. Yeah. Binary multiplication can be implemented as a sequence of shifts and add instructions. Here, shift and add instructions. Given two registers y, x and y, and an accumulator register a, the product of x and y can be computed using algorithm 1, When applying the algorithm, it is important to remember that in the general case, the result of multiplying an n-bit number by an m-bit number is at most n plus m bit. That generally is the result of multiplying an n-bit number by m-bit number is at most n plus m bits. For instance, 1 into 1 2 bit, the result is takes 4 bits. Therefore, when applying algorithm 1, it is necessary to know number of bits in x and y. Since x is shifted left on each iteration of the loop, the register used to store x and e must be at least as large as the number of bits in x plus the number of bits in y. That makes sense. To multiply two n-bit numbers, you must be able to add two 2 n-bit numbers. Two n-bit numbers, okay. Adding 120 because the accumulator can grow up to 2n and x can also grow up to 2n, and then you are at a point adding them both. So a is 2n long, 2n bits long, and x can also be 2n bit long after left shifting it multiple times. Adding 128-bit numbers requires to add instructions, and the carry from the least significant 64 bits must be added to the sum of the most significant 64 bits. AArch64 provides a convenient way to perform the addition with carry. Assume we have two 128-bit numbers x and y, where we have x in 0 and the first register and y in second and third register, where the high order words of each number are in higher number. So that therefore LSB in 0 and MSB is in the first registers, and we want to calculate x in the x number. We wanted to update x by adding y to it. Listing 7.1 shows a two instruction sequence for an AArch64 processor. The first two instruction sequence, because when to do this thing this was also a problem given to us in a previous chapter, and we did not do it in just two instructions. It took us quite a few instructions. Listing 7.1 shows two instruction sequence for an AArch64 processor. The first instruction adds the two least significant words together, the two least significant words together, and sets or clears the carry bit and other flags in the P state. The second instruction adds we add the contents of this, both the LSBs from both the numbers, and save it to X and add them, and this S signifies that we are updating the flags in the program state register, P state register, at the low order double words ash a set flags in P state, and then add and also add the carry. If there is a carry, also add that, and if not, then do not add that. That makes sense. Adds the two most significant words along with the carry bit. This technique can be extended to add integers with any number of bits. Yes. So add the LSBs and then add the MSBs with the carry. Binary multiplication using algorithm 1. Algorithm 1, okay. Whoa. Shift only. We have x0, therefore we only shift x, and we shift a and it is 0, so nothing. Now we have 1 here, so we add and then shift. We add this to this, and then so we have this and we shift x. Shouldn't we also shift a? No, we do not shift a. No. We do not shift a, we only shift x. Yes, that makes sense. And we shift y. Then we have a 0 here, so we only shift. This becomes this, and now we have 1. So we add this to this, and then we shift x. we get x as this at the end, and this added to this becomes this, and we do the same. Okay, binary multiplication using algorithm 1. Assume we wish to multiply two numbers, x equals this and y equals this. Applying algorithm 1 results in the following sequence. That makes sense. Now the assembly code for the same is going to be crazy. On an AArch64 processor, the algorithm to multiply two 64-bit unsigned integers is very efficient. The algorithm to multiply two 64-bit unsigned numbers is very efficient. String 7.2 shows one possible algorithm for multiplying two 64-bit numbers to obtain a 128-bit result. The code is a straightforward implementation of the algorithm, and some modifications can be made to improve efficiency. For example, if we only want a 64-bit result, we do not need to perform 128-bit addition. And this significantly simplifies the code as shown in listing 3.2. Here we have two numbers x and y. We want to add them, and then we have a message which will print the result. Here is a loop and stuff. God damn it. First, let me see how long this chapter is. Not long. Like, the binary multiplication part is not that long. But how long is the binary division part? Division is going to be great. We will start division today, right? Maybe we can finish multiplication and division both today. Let's see, this is a 700 line long C program which does something that is just crazy. 700 line C program. Then we have chapter. Okay, we can multiply complete multiplication and division just today. That is going to be cool. Where were we? Here. Okay, let us write this code. Let me go to the folder where I write my assembly programs, and now here, and multiply by adding dot s. Here first I need to specify the number called x, which will be a 64-bit number, therefore a quad, and the value and that it stores is a, b, c, some number, and y is also a quad. It stores hexadecimal number f, h, a number, and then we would like to also print the result after it, and so we will call it format and percent ln. I guess it is ln to print a long number. Is it ln? What was it here? lx multiply by, let's say, lx. It gives us lx and then new line. Now in the dot text we say that we have a thing called main, which is global and align by 2 bytes, and then we will define the main function, the main label. First of all, we will store the stack, the frame pointer, and the link register onto the stack like that. And then after that, I would like to get the values of x and y over here in the 0th and the first register. For that, I will get the address into the 0th register for x. Um, Page, and that is the right format, right? Yep. And then add to the 0th register the x page offset. That is the right format. Shit. Let me check what the heck. It is at the rate, not a semicolon. At the rate. At the rate. Okay. Now let me load. Ah, shit. Now I have the address for x in the 0th register. Now I will load the value into the 0th register whose address is in the 0th register. Now I will do the same for y in the first register. Add to x1 first register the page offset for y and then load it there. Now I have both the values x and y, and now I would like to multiply them by a loop. And let me also initialize the accumulator register in the secondary register. Let's say starts with 0, and here I will declare a loop label which will check, compare. No, no. This will be a post loop, so I will check at the end, compare the contents of the first register, that is y, with 0, and branch if not equal, then branch back to the loop. That is, the loop starts again. And what do I do in the loop? In the loop, I have to compare the LSB of the yth register. How do I get the LSB of the y register? How do I get the LSB of y register y? Take its AND with something. Yes, take its AND with 1, right? And store it into the third register, and I will take the AND of the first register with 1. So now in the third register I should have 0 or 1. If it is 0, then I do something, and if it is 1, then I do something else. Compare register 3 with 1 and conditionally select and save into the I want to conditionally okay, the thing I'm going to add, can I conditionally add? Think I can. Nah. Okay, let me do this. In the fourth register, I will get the value that is to be added to the accumulator. It will either be 0, or it will either be the contents of the 0th register. So, what is the equation that I'm trying to check? The condition is equal. So, if the third register contains 1, that is, if third and 1 are equal, then I will put the contents of 0th register, that is x, into the 4th register. Otherwise, I want to put there 0. What is the 0th register? Yes, register in AArch64. How do I call the 0th register? XZR. Um, 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 is that the way that I can call it? XDN this shit. The zeroth register XZR and WZR always reads as 0, so I can do XZR. XZR. Okay. If the third register contains 1, then I uh, put the X number into into the fourth register. Otherwise, I put 0 there, and then I add to the second register, which is our accumulator register, and store it in the second register, the sum of itself and the fourth register. And then I would like to logically shift left the contents of the X register by 1 and save them into the first register, and then logically shift right and save into the first register the contents of the first register. And this should give me the answer. I'm adding things to the accumulator based on the LSB of the first register, and I'm also left shifting the X number and right shifting the Y number, and this will go till Y becomes 0. If it becomes 0, then I will exit the loop and I will be here and I will have the answer in the second register. Now I would like to print the answer. For that, I will get the address of format string by getting the page address in the 0th register. I can lose the 0th register, the contents of the 0th register. That does not matter now. And yeah, get the address, page address of FMT and add to it the page offset. Now I have the address of the string that I want to print, and god damn it, I cannot lose the original numbers. Let me put them somewhere else. Um, After getting them, let me put them in the 5th and 6th register. I'm not using them later. So move into the 5th register x0 and move into the 6th register x1. My stream working? Yes. It just gets stuck at some point. I don't know why. Now, in the 0th register, I have what I want. I have the first parameter that I will pass to the printf function. Now, I need to pass on 3 64-bit numbers onto the stack. Right, the numbers themselves, not anything else. So, the okay, let me get subtract from the stack pointer what 32 8 8 8 is 24. Let me get 32 bits, and then I will first of all store the first number, which is store the contents of x. X is in the 5th register, just add the stack, right, and then store the contents of the 6th register, that is the the content, that is the y number, and then store the answer, which is in the 2nd register, onto the stack with an offset of 16, and then at the end call the printf function. And after doing that, I have everything. Then I can move into the 0th register x0 0, and I would like to add to the stack point. I have to add, not like to, I have to add to the stack pointer 32 the number of bits that I took from the stack, and then uh, load the frame pointer and the link register from the stack like that, and then I can just return. Now this should work. lang multiply and store the output in dot out. Unexpected token. Oh yes, H does not exist, right? Yep. H does not exist in hexadecimal numbers. Now clang and it works. Whoa, I see the answer. Is this the correct answer? Can I do this multiplication here? 1FBF0. Nah. Um, hex, hexadecimal numbers. Hex calculator. One number is this, and the other is this. Calculate, not add, but multiply them. Multiply. The answer is this. Yep. 154F0. 154F0. DED0. Dead 0. Yep. That is working correctly. Okay, so we do not have to read all this. We wrote the program ourselves. Now, signed multiplication. Okay, that was for unsigned multiplication when we have absolute values, but now it can also be signed. The number can be negative. Consider two multiplication problems shown in figure 7.1, this, and figure 7.2. Note the result of a multiply. Here we have negative number being multiplied by this, and this number is signed because this has one. This number is negative. This has one at the start, and this is not. And then multiply. What the heck? Um, what is when I multiply 1 by this, why do I get this long ass number? Because I do, I get signed extend. I am extending this number, signed extending this number. Okay, and okay, I'm sign extending and then left shifting the contents of the X register. Okay, okay, that makes sense. For this reason, note that the result of a multiply depends on whether the numbers are interpreted as unsigned or signed, or signed, unsigned numbers, or signed numbers. For this reason, most computer CPUs have two different multiplication operators for signed and unsigned numbers. And here we have this number where these are not negative, and when these are not negative, I do not sign extend them. I normally extend them. Okay. If the CPU provides only a unsigned multiply, then a signed multiply can be accomplished by using the unsigned multiply operation along with a conditional complement. A conditional complement. The following procedure can be used to implement signed multiplication. Okay. If the multiplier is negative, multiplier, that is y, is negative, take the 2's complement. Okay. If the multiplicand is negative, take the 2's complement. Okay. And perform unsigned multiplication. Okay. And if the multiplier or multiplicand was negative, but not both, take 2's complement of the result. Okay. Signed multiplication using unsigned math. So we want to multiply this and this. So first we get 2's complement for this number. We get the 2's complement for 39, and we do this, and then we get the 2's complement for the result, which is this. Okay. Now, multiplication of a variable by a constant. Multiplication of a variable by a constant. If x or y is a small constant, then we don't need the loop. We can directly translate the multiplication into a sequence of shifts and add operations. This will result in much more efficient code than the general algorithm. For small constants, this method is often faster than using a hardware multiply instruction. If we inspect the constant multiplier, we can usually find a pattern to exploit. If we inspect the constant multiply, we can usually find a pattern to exploit that will save a few instructions. For example, we suppose we want to multiply a variable x by base 10. The multiplier base 10 means this. So we only need to add x to itself by left shifting 1, and after left shifting it thrice. To left shift it thrice as shown below. Yep. Get the address of x and then load the value into x, then left shift the contents of x by 1 and add to the x register and store in the x register the contents of x left shifted by 2. Okay, now suppose we want to multiply a number x by 1110. We want to multiply a number x by 11. The multiplier is this, so we will add x to itself, left x to x shifted left by left 1 bit plus x shifted left 3 bits as shown here. Yes, if we wish to multiply by a number, let's say 1000, then we know that 1000 this, it looks like we need to shift 1 shift plus 5 shift operations or 6 shift operations. With a little thought, we can reduce the multiplication of operations, and I know how. We get we shift the contents of the X register first by 3, and then we subtract. Yes, we subtract, right? Nah, we do not. We can subtract after shifting the contents 1 byte, and then add after shifting the contents this many bytes. Okay, but let's see. Get the number x, and then we add. Okay, in the zeroth register, first register, we have the number, and we want to multiply it by this thing. And then in the first register, in the zeroth register, we store the sum of the number and its content left shifted by 1, which is which. Why are we doing that? Shift and add x0 equals x3. The contents of the third. Okay, I think this should be 3. This should have been 3, I suppose. Yep, this should have been 3. And then we add to x the after shifting x by 2 bits. That is for this one, for this bit. And then we add 2x and the contents of 1, the original number, after shifting x left by 1. Why are we adding the original number now? 3x plus 3x into 4. 3 into 4 is 15 here. Load x, and why is this 3x? How did we multiply the number by 3? Multiplying the number by 3. How did we multiply the number by 3? By left shifting and adding to itself the number. Oh, Okay. We multiplied the number by 3. Okay, by doing this. Okay, that makes sense because we got the original number and then we left shifted it and we added it to itself. That is means 1 1. We multiplied it by 1 1 and 1 1 is 3. So we got 3x, and then here we added the number to itself to itself after left shifting it twice, and left shifting twice means multiplying by 4. We got 15 here. And then we added x and left shift, and we added x is in this, and then we left shifted the contents of this x, and it's 15 into 2, and we got x 31x here at this point, and then we left shifted by 5, that is multiplying by 32. We got 992, and then we added 8x to 992x, and we got 1000x. Okay, that is also chill. Applying the basic multiplication algorithm to to multiply. I think we can do this a little better. If we multiply, we can multiply the number by. Okay, let's go with this. What they did, applying the base multiplication algorithm to multiply a number x by 2 to 5, 10. Wouldn't that be just left shifting by 5? No, left shifting by 8. Let's see. No, it would have been 2 to 6. Yeah, if we wanted to left shift by 8, would result in 7 add shift operations, but we can do it with only 3 operations and use only one register as shown here. In the 0th register, we have the number, and then we left shift 0. So this becomes 3x, and then we multiply 3x, add to 3x. Left shifted value of 3x, that is 4. So we have 3 into 4 plus 3, that is 15, and 15 into 15 plus 15 into 16, we get 22255. Okay. Most modern systems have assembly language instructions for multiplication. However, on most processors, it is often more efficient to use the shift, add, and subtract operations when multiplying by a small constant. The AArch64 processors have a particularly powerful hardware multiplier. Okay, they can typically perform multiplication with a 64-bit result in one clock cycle. That is crazy. Multiplication of a large number in one clock cycle, they can calculate the multiplication with a 64-bit binary result. How would that work? Okay, they are very hardware efficient, it seems. The long multiply instructions take between 3 and 5 clock cycles, depending on the size of the operands. Using the multiply instruction on an AArch64 processor to multiply by a constant requires loading the constant into a register before performing the multiply. Therefore, if the multiplication can be performed using 2 or fewer shifts, add or subtract instructions, then it will be equal or better than using the multiply instruction. Therefore, if the multiplication can be performed using 2 or few shifts, add, and subtract instructions, then it will be equal or better than multiplying instruction. Multiplying large numbers, then we just move on to binary division. That is just crazy, and it hasn't even been 1 hour. Yeah, 44 minutes. That is, and my stream is working. Stream is working. The screen has not stuck. The screen is not stuck. My bad. Pardon. pedantic. Consider the method used for multiplying two-digit numbers in base 10. In base 10, yep. Using only the one-digit multiplication table, figure 7.3, which is these. No, no, no. 7.3. What the heck? What the heck? Figure. Wait, what? I don't. Yeah, this. The multiplication of these two numbers would be equal to, if I multiply this bit by this bit and left shift this bit, add these two and add these like that, product of this. Yeah. Okay. Uh, yep. Table figure 7.3 shows how a two-bit digit a equals a1 and this is multiplied by another two-digit number b to produce a four-digit result using basic multiplication operations which only take one digit from A and one digit from B at each step. This technique can be used for numbers in any base and for any number of digits. Recall that one hexadecimal digit is equivalent to exactly four binary digits. If A and B are both 8-bit numbers, then they are also two-digit hexadecimal numbers. Two-digit hexadecimal numbers. Yeah. In other words, 8-bit numbers can be divided into groups of 4-bit. 8-bit numbers can be divided into groups of 4 bits each, where each representing one digit in base 16. Given a multiply operation that is capable of producing an 8-bit result from two 4-bit inputs, the technique shown above can then be used to multiply two 8-bit numbers using only 4-bit multiplication and operation. Okay, that is going above my head. This technique can be used for numbers in any base and for any number of digits. This is a technique. First digit, MSB, LSB, MSB, LSB. Okay, and multiply the LSBs, and that will be equal to the LSB. And add, if there is any carry, to MSB multiply by LSB and LSB multiply by MSB. And left shift that once and add, that would be the second and third digits. Yep. And then we multiply the MSBs after shifting them twice and add all the results. Okay. This technique can be used for numbers in any base and for any number of digits. Recall that one hexadecimal digit is equivalent to four binary digits. Recall that one hexadecimal digit is equivalent to exactly four binary digits. If A and B are both 8-bit numbers, then they are also two-digit hexadecimal numbers. In other words, 8-bit numbers can be divided into groups of 4 bits, each representing one digit in base 16. Yes, given a multiply operation that is capable of producing an 8-bit result from two 4-bit inputs, the technique shown above can then be used to multiply two 8-bit numbers using only 4-bit multiplication operations. Given a multiply operation that is capable of producing an 8-bit result from two 4-bit inputs, the technique shown above can then be used to multiply two 8-bit numbers using only 4-bit multiplication operations. Okay, so instead of multiplying two digits by two digits, I am multiplying one by one and using that to calculate the multiplication of two digits by two digits. Okay, carry this one step further. Suppose we are given two 16-bit numbers, but our computer only supports multiplying 8 bits at a time and producing a 16-bit result. We can consider each 16-bit number to be a two-digit number in base 256. We can consider each 16-bit number to be a two-digit number in base 256. Okay, and use the above technique to perform four 8-bit numbers to perform four 8-bit multiplies with 16-bit results. Then shift and add the 16-bit results to obtain the final 32-bit result. This technique can be extended to perform multiplication with any number of bits, even with limited hardware multiplication instructions. Okay, here we are dividing two digits into one, and let's say we have 10 digits, then we can say the first five digits are represented by a single character and the last five digits will be represented by a single character, and we can multiply those two things together and get a result. Okay, that is cool. Now binary division, and we are at page number 199. That is crazy. And then when will we have abstract data types? We will have abstract data types, begin abstract data types at page number 112. So we got multiplication for today. Easy. And it is not even like really big. Most of it is code. Binary division can be implemented as a sequence of shift. I do not understand how division is performed at binary level. Binary division can be implemented as a sequence of shift and subtract operations. When performing binary division by hand, it is convenient to perform the operation in a manner very similar to the way that decimal division is performed. As shown in figure 7.4, the operation is identical but takes more steps in binary. This is 7.4. This is the way we divide numbers. We want to divide this number by this. We multiply 13 by 9 and we get this, and we can multiply 13 by 9 using addition and shifts, and then we subtract, then we repeat and do things. Okay, this is what we have been reading throughout our life in school. Now, division by a power of 2. If we want to divide by a power of 2, we can simply right shift by that much. If the divisor is a power of 2, then division can be accomplished with a shift to the right. Using the same approach as was used in section 7.2.1, it can be shown that a shift right by n bits is equivalent to division by n power 2 power n. However, care must be taken to ensure that an arithmetic shift is used if the dividend is assigned two's complement number, and a logical shift is used if the dividend is unsigned. That makes sense. Then we have something division by a variable. The algorithm for dividing binary numbers is somewhat more complicated than the algorithm for multiplication. The algorithm consists of two main phases. The first phase is to shift the divisor left until it is greater than the dividend. Shift the divisor left until it is greater than the dividend. What is a divisor is okay. What is divisor and dividend? Quotient is the answer. The divisor is the number that divides another number, and the dividend is the number that is being divided. Okay. The algorithm consists of two main phases. The first phase is to shift the divisor left until it is greater than the dividend. To left shift the divisor to first left shift the divisor left until it is greater than the dividend. Okay, that is equivalent to shifting the dividend right. Okay, and count the number of shifts. The second, okay, that I guess makes sense. The second phase is to repeatedly shift the divisor back to the right and subtract whenever possible. And subtract. Okay, so the thus we get the highest number, right? Here, when we are doing this, we take this number and keep moving it to the right, to the right, to the right, keep shifting it left. And when we were at this point, some point here, then this became greater than this, and then we started shifting it right, and we would subtract it whenever possible, and we shifted this number right once, and then we subtracted from this, and this is what we got. So we did the same thing with this. Okay, that is intuitive in a way. Yeah. The second phase is to repeatedly shift the divisor right back to the right and subtract whenever possible. Figure 7.5 shows the algorithm in more detail. Before we introduce the AArch64 code, we will take some time to step through the algorithm using an example. Let us begin by dividing 94 by 7. What is 94 divided by 7? 13. Yep, 13, and the remainder is 3. The remainder is 3. Yes. Yeah, 3, and the answer is this 13? 1 plus 4, 5, 5 plus 8, 13. Yep. Now, this is the algorithm. Now, yeah, return result. Start, set counter to 0. Okay. And then here we have divisor greater than, less than dividend. And if it is not, then I increment counter, shift divisor left by 1 bit. Go here, increment counter, shift, okay. Then here, we see if counter is less than 0. If counter is less than 0, then I return the result. Otherwise, that is the count is negative. Okay. Otherwise, no, when it is not great, less than 0, it is 0 or something, then divisor, then I will check if divisor is less than equal to dividend. Divisor is less than equal to dividend. Okay, and if it is, then I shift 1 into LSB of quotient. Shift 1 into LSB of quotient. And if it is not, then I shift 0 into LSB of quotient. Into LSB of quotient. Okay. Okay. LSB of quotient, I shift 0 there. If it is not, okay. Yes, makes sense. And then when I shift 1, when I subtract divisor from dividend, and after that decrement count and shift divisor right. Divisor, shift divisor right, and decrement the counter by 1. And I could be doing this forever and ever, forever and never. Stay in my heart. And the last I will either get 0 or 1 and return result. Okay. Here, to implement the algorithm, we need three registers: divisor, dividend, and counter. One for the dividend, one for the divisor, and one for the counter. The dividend and divisors are loaded into registers, and the counter is initialized to 0 as shown below. And then we have our algorithm working. We will be reading about algorithms next year, I guess. Yeah. Then we have, and next the divisor is shifted left and the counter incremented. Without reading it, let's see what is going to happen. First, we will shift the divisor left by 1 and increment the counter by 1 and check. But before checking, we check before shifting. First, we check if the divisor is less than the dividend. It is. So we left shift the divisor and increment the counter by 1. Yep, we left shifted the divisor and incremented the counter by 1. Then we will check again if the dividend is less than the divisor. It is not. Then we left shift the divisor again and increment the counter by 1 again. Yep. And we do the same till the divisor is greater than the dividend. And at this point, the divisor is actually greater than the dividend. When this happens, what will we do? We will, okay, here is what is going to happen. We will right shift this once and subtract the divisor from the dividend and save that into the dividend and decrement the counter by 1. So, and yes, we have a quotient. When this becomes less than dividend, we will add 1, and so we will also add 1 here. At this point we added 1. So first, we this is the same as this here, and then we subtracted 1 from the counter and we left shifted the divisor and we added 0 to the quotient. And then we see that the dividend is greater than the divisor. Therefore we subtract from the divisor and add 1 here and subtract the counter. We got this, and the quotient became 1. And then we compare these. We see that the dividend is greater than the divisor. Therefore we will in left shift the quotient by 1 and add 1 add 1 to the quotient and subtract 1 from the counter, and then left shift the divisor, and whatever the result is after subtracting, we will put that in the dividend like this. And then we see that here the dividend is lower than the divisor. Therefore we will left shift this one and this once and add 0 at the start like this, and we will subtract 1 from the counter. We subtract 1. After that, what do we do? Yep, we subtracted 1, and then we compare them again. When we compare them, we see that this is greater, therefore we put 1 in the quotient. After left shifting this once, we do this and we right shift this once and we decrement the counter, and now we see that the counter is negative. That is all our ones. Therefore we are finished, and this is the answer. Let's read. Next we allocate a register. Wait, we do all of this, and next we allocate a register for the quotient and initialize it to 0. Then according to the algorithm, we repeatedly subtract. If possible, shift to the right. We repeatedly, if next we allocate a register for the quotient and initialize it to 0. Then according to the algorithm, we repeatedly subtract. If possible, shift to the right and decrement the counter. This sequence continues until the counter becomes negative for our result. This results in the following sequence. Yep, we did saw all of this, and this is what happens when the algorithm terminates. The quotient register the quotient register contains the result of the division, and the modulus remainder in the dividend register. Dividend register contains the remainder. Thus, one algorithm is used to compute both the quotient and modulus at the same time. There are variations on this algorithm. For example, on variation is one variation is to shift a single bit left in a register rather than incrementing a counter. Okay, this variation has the same two phases as the previous algorithm but counts in powers of 2 rather than by ones. The following sequence shows what occurs after each iteration of the first loop in the algorithm. Power of 1, 1, 1, 1, 1. This divisor is greater than the dividend, so the algorithm proceeds in the second phase. In this phase, if the divisor is less than the equivalent, then the power register is added to the quotient. And the power register is added to the quotient and the divisor is subtracted from the dividend, uh, like usual. Then the power of divisor register are shifted to the right. Yes, the process is repeated until the power register is 0. The following sequence shows what will happen in the register at the end of each iteration of the second loop. We have this. The power register is like only 1. So yeah, we can add that to the quotient, like here. Yeah, that makes sense. Now, as with the previous version, when the algorithm terminates, the quotient register contains the result of the division and the modulus remainder is in the dividend register. Listing 7.1 shows AArch64 assembly code to implement this version of the algorithm for 64-bit numbers and the counting method for 128-bit numbers. Okay, let us write shit our own program and okay, we will write our own program which divides numbers, right? Divide by subtracting dot is here in the data section. I will have two 64-bit numbers. That is x. X would be take up a quad of space, and the number would be a large number. And since it is 64 bits, that is 8 bytes. One byte is represented by two hexadecimal digits. Therefore, I can use 16 hexadecimal digits to represent this number. How much did I use already? 1, 2, 3, 4, 5, 6, 7, 8. I guess that should be enough. And y, I will have another number. This one will be small. And then a format string to print the result in the ASCII's format. ASCII's format. I will have percent long extended. I guess that is what it is called, extended. I do not have the divide sign to I know. And then percent %lx equals percent %lx. The new line. Now in the text section, I will tell that I have a thing called global. Global, a main level can be accessed globally. Then I will align at 4 byte space and then define the main global. First of all, I will save the frame pointer and the link register like any human being would by pre-incrementing the stack pointer, and then the fun begins. I will get into the 0th register the x number which I will first get the page address for it, page, and then add to the 0th register the offset for it, and then load into the 0th register the value at the memory location whose address is stored in the 0th register. Now I will do the same with the y value and get it in the first register by first getting the page address and then adding to the page address the page offset, and then I will load into the first register the value and the memory location whose address is stored in the first register. Now I have both the values x and y. What will I need? I will be needing a counter register. Let me use x2 as the counter register, and I will also be needing a quotient register which will come later. But now here is the first stage, first part. What do we do in the first part? First of all, I will compare them. Compare this first register and the second register contents. Yes, compare them, and if greater than first register contains a big number. Yep, this should wait. So if the dividend is less than the divisor, then I go to the second phase. But if it is not, then the first phase starts. And in the first phase, I logically shift left and save to the first register by 1 and yeah, increase the counter. Add to the second register, which is my counter 1. Yes. And then I will again compare the contents of the 0th and the first register. If the contents of 0th register, that is the dividend, is still greater than the first, then I will branch to the first. Now here we have the implementation for the second. What do I do here? In the second, let me compare the contents of the second register, which is the second register. What is the second register? The second register is the counter with x, z are 0, and if oh, yes 0, and if branch if less than, if the counter is less than 0, then I will branch to end. And here I would also like to do move in the third register 0, that is initializing the quotient to 0. Now if it is not 0, the counter is not 0, then I will see. I would like to do a few things. First of all, I would like to compare these two, that is the dividend and the divisor, and conditionally not just select but conditionally do a few things. I will, of course, without a doubt, have to logically shift left the contents of the third register, that is um, the quotient by 1, and then I would have to conditionally increase the contents of the third register by 1, And what is the condition? What is the condition that I am checking for? If I want to increase only if the dividend is greater than the divisor. That is greater than. Yep. Then increase it. Okay. And what are the other things that I have to do? Well, I would have to for sure decrease the counter by 1 in every case. And what else? Right shift the divis. But before right shifting, I will conditionally have to subtract from the divisor, from the dividend, the current value of the divisor. So let me use the fifth register to store the subtraction. Can I use the fourth register? Is it empty? Yep, it is empty. I will store in the fourth register the division, subtraction of the zeroth register and the first register, and then conditionally select and store in the zeroth register, which is the dividend, either x4 or its current value based on what is the condition, if greater than, if the contents of dividend is greater than the contents of the divisor, I will store the new subtracted value and then logically shift left the contents of the first register by 1, and then at the end branch to second, and then here I have end. What does end do? End moves in the zeroth register. Nope. End has to first of all print the result, and for printing the result, where is the result? Where is the one-time result? The result is in the third register, and what is the result is in the third register, so I will put that on the stack, and I need the original numbers too. So let me at this point, after getting them, save the original numbers in the fifth register. I'm not using the fifth register, and in the sixth register. Yep, and then I will store all of these onto the stack by getting on the stack some 32 bits, 32 bytes, and then storing. I can store two at a time. Store the fifth and the sixth register. Yep, that is absolutely correct. Onto the stack, and then store the third register onto the stack with an offset of 16. 16, yes, and wait, with an offset of 16, and yep, move. Nope, I will now get the address in the zeroth register for the format string, which is to be passed on to the printf function as its first argument. So for that, I have to get first the page address and then add to the zeroth register the page offset. Yep, yep. And I can simply call the printf function and then exit with an exit code of 0. That should work. I hope it works. The output should go to output. Okay. Or it is not XZR, it should be. It is not ZXR, it should be XZR. Divide page number line number 37 here. Now Clang, no errors. It works. Let me check. This number, hexadecimal division. Shit. Hexadecimal division calculator, hex calculator. I want to divide from this number. What is the other number? 1BC, 1BC, and the value seems to be A7EE. That is not this. This is wrong. Shit. The heck? Are the inputs correct? 1BC, 1BC. Yep, they are correct. Shit. The answer. My implementation is wrong. And I did not. Why did it not end? Why did the program not end after printing? Okay, so we have a few errors. I did not store back the stack pointer and that. Load pair the frame register and the link register. And before that, let me give back what I took from the stack by adding to the stack pointer the number 32. And in this line, I will add, just stack pointer and then increment by 16. Now, this should at least exit at the end. Yep, it does exit. But the answer is wrong. The answer is wrong. It should not. So, first of all, I am doing all of this. Let me do, instead of that, big ass numbers. Let me do 10 divided by 2. Is 0. It is not actually. Let's say 10. It cannot be 10. 10. That was not 10. That was 16, I guess. Yeah, that was 16. And because it was in hexadecimal. 8 divided by 2 is 0. That is pretty wrong. A little off the mark. Mark Norman. Yeah. Or Norm McDonald's. Yeah. Okay. First, we are getting the dividend here in the 0th register, and then we are getting the divisor here in the first register. Okay. That much is explanatory. Makes sense. And then we are storing the divisor and the dividend in the 5th and the 6th register, and then we are initializing the counter and the quotient. Am I printing the wrong number? There. What does C increase? Conditionally increase the 3rd register. That makes sense. Yeah, that would make sense. Am I not left shifting the contents of the 3rd register? Nope, I am left shifting the contents. And then at the end, I am working fine. But what is the problem then? The first loop is good. Let's go with 8 and 2. Let's suppose that in the 0th register we have 8 and in the first we have 2. Then we compare them. And if they are less If 8 is less than 2, then we go to the second, but it is not actually, as it turns out, 8 is not less than 2, so we go to the first level, and here we left shift the 2 by 1, that is we get 4, and then we add 1 to the counter, okay, and then we compare them again, and if 8 is now greater than 4, we go back to the first, okay, and then here we left shift again, we get 8. God damn it. Yes, we get 8. If it is perfectly divisible, what would happen then? That is a good question. If our answer is perfectly divisible, what would happen then? That is a good question. Not just greater than. Yeah, if it is greater than, then is the only time then that you should go. So now at this point they are both 8 and the counter is 2. And we get down here. We compare the counter with 0. If it is less than 0, then we go to end. But if it is not, it is 2. So we move on here. And we left shift the third register by 1, which is just 0. 0 left shifted by 1 is still 0. Then we compare first and 2. Not just greater than, but equal to. That should fix a few things. And this too should fix a few things. Okay, yes. Even if these numbers are greater than or equal to, I will do this, and yes, this should now work. And we division the original numbers, the ones that were messing up this number. Do not look down. And here we had one BC. Now let's do 36 FFF. That is still wrong. This is the value that I'm providing to this, and this. Is this too long? I can use 60 numbers, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It is not too long. Let me do, not drawing it. Get back to my function and shorten this number a bit till 4. Okay. My output is 0, which is of course wrong. Definitely wrong. Shit. Remove one more 4 and see the answer. It is certainly not a 0. It is this A7EE3 and remainder is 80. Um, let's do what? It is working fine for one digit. Let's do 100 divided by 2, which should give us 8 because 10 is 16, and I guess it will give us 0. It does give us 8, so it is working correctly. When are the times that when it is hallucinating, not giving? What are the bottlenecks? What are the edge cases where this might mess up stuff. 1,000,000 divided by 13. That is a bottleneck. Ah, shit. 1,000,000 divided by 13 and calculate. The result is D7. In binary decimal, it is this number 4096 divided by 19, and the result is 215. But I am getting 0. So, yeah, that should not happen. Dividend subtraction. Is it because of the way that I'm printing them? If I write 10 here, will I get them in decimal? I did not. It just made them 10, made them take 10 digits. Okay. I have 1,000 there. What is 1,000 in binary? Ah, shit. First, I am left shifting it. Why I keep left shifting the first by 1, right? And the only time that I am incrementing the quotient is when the contents of the first register are greater than or equal to 1. Okay, that should work. I conditionally increase here this, and then I subtract, get the subtraction in the fourth register. Yep, and then I conditionally update the 0th register either with the value of which I just got after subtracting in the fourth register, or keep its original value. If because of this comparison. Hmm, And then I logically left shift the contents. God damn it. Logically shift right. I have to logically shift right the divisor. Yeah, my bad. This should work now. D7. D7. And what was the original big ass number? This and this was 1 BC. It was totally randomly 1 BC. And we do get A7 triple E. So yeah, that was the problem. We were left shifting the divisor instead of right shifting it. And we do not have to read the code because we wrote it ourselves just now. The pretty big ass code. And we can always come back to this, right? And yeah, that is good. Division by a constant. And this is, I guess, the last part in the division part. Nope. Then we have division by large numbers. And then That's it. Dividing by large numbers is the last part, but before that we have this division by a constant. Yep, the stream has not stuck. Let me show you something. Nope, not this, but yep, center stage. But see that this is supposed to follow me. If I go two back, then this is supposed to zoom onto my face, but it is not. Yes, here I am in the middle. I should turn it off. This might zoom my face when I do not want it to. Yep. Now, division by a constant. In general, division is slow. AArch64 processors provide a hardware division instruction which requires multiple clock cycles to produce a result depending on the size of the operands. Some older ARM v7, the late older version, older, yeah, right, older, now is the v8. Processors must perform division using software as previously described. In either case, division is by far the slowest of the basic mathematical operations. However, division by a constant can be converted to a multiplication by a reciprocal of c. Yes, yes. It is obviously much more efficient to use a multiply instead of a division wherever possible. Efficient division of a variable by a constant is achieved by applying the following equality. Mm, this divided by this is equal to divided by c is equal to x multiplied by 1 upon c. Yes, the only difficulty is that we have to do it in binary using only integers. If we modify the right hand side by multiplying and dividing by some power of 2, we can rewrite equation 1.7 as this and okay, multiplying this by this, we call that in binary division. 2 power n is the same as left shifting by n bits, yes, while multiplying by 2 power minus n is done by right shifting by n bits. Therefore, equation 7.2 is just equation 7.1 with two shift operations added. The two shift operations cancel each other out. Now let m equals 2 power n divided by c. Okay, we are taking this part as m and we can rewrite equation 7.2 as this. Yep, we just have to find out m and multiply that by x and then right shift the product by n times. We can now have a method of dividing by a constant. Oh, since we have a constant, therefore we can know m beforehand because we have m is a constant, and then we can just multiply x by m and right shift the result. C, which involves multiplying by a different constant m and shifting the result. In order to achieve the best precision, we want to choose n such that m is as large as possible with the number of bits we have available. Okay, and because 1 upon c can take 1 upon, we want 1 upon c will not be an integer and we want it to be an integer. That is why we are multiplying that it by 2 power n to make it an integer m, such that m is as large as possible with the number of bytes we have available to have the best precision. Yep, to have the best precision, we want to make m as large as possible. Suppose we want efficient code to calculate x divided by 23 using 8-bit signed integer multiplication. Our first task is to find m, which is 2 power n. 2 power n is 8. 2 power 8 divided by 1 by m multiplied by divided by c is equal to m, such that this M is less than all of this and greater than all of this, greater than equal to this. But why do I have one here? Because we want it to be largest. In other words, we want to find the value of n where the most significant bit of m is 0, that is, it is positive, and the next most significant bit of m is 1. If we choose n equals 11, then this equals this in binary. Rounding to the nearest integer gives m equals 89. In 8 bits, m is this, or 59 in 16 bits. We now have values for m and n, and therefore we can apply equation 7.4 to divide any number x by 23. The procedure is simple: multiply x by m to get a number, and then y left shift y by 11 bits. However, there are two more considerations. First, when the divisor is positive. When the divisor is positive, the result for some values of x may be incorrect due to rounding error. Okay, that is acceptable. It is usually sufficient to increment the reciprocal value by 1 in order to avoid these errors. The reciprocal, okay. In the previous example, the number would change from this to this, 9 to 5a. Multiplying by 2, okay, in the previous exam, okay, it is usually sufficient to increment the reciprocal value by 1 in order to avoid these errors. We can increment, okay. When implementing this technique for finding the reciprocal, the programmer should always verify that the results are correct for all input values. The second consideration is when the dividend is negative. In that case, it is necessary to subtract 1 from the final result. It is necessary to subtract 1 from the final. Okay, these are just seem to be random, not random. There must be some reason for why they are saying all this. And no one is watching my stream. In that case, it is necessary. No one. That is fine. I have abandoned my child, Daniel Day-Lewis. Gleam. Okay. For example, to calculate 101 in base 10 divided by 23 in binary with 8 bits of precision, we first perform the multiplication as follows. Multiply this by this, and what is this? This is m, which you got right here. And this 5a and 5a. A means 10, and 10 is this in binary, and 5 is this in binary. So we multiply them and we get this result. We will left shift, right shift the result by 11 bits. The result then shift the result by 11 bits. This shifted right 11 bits is equal to, which is 100 in base 10, which is 4 in base 10. If the modulus is required, it can be calculated as 101 mod 203. How? 101 minus 4, that is the result we got, into 23. We get 9. 9 is the remainder. Okay. Which once again requires multiplication by a constant. Which once again requires multiplication by a constant. Okay. In the previous example, the shift amount of 11 bits provided the best precision possible. Yes, but how was that number chosen? Because that makes sense. How was n chosen? In the previous example, the shift amount of 11 bits provided the best precision possible. But how was that number chosen? The shift amount n can be directly computed as this: p, where p is the desired number of bits of precision, p minus 1, and less lower limit. This is the symbol for lower limit for log c at base 2. Okay, where pre is the desired number of bits of precision. The value of m can be computed as this 2 and if c is greater than 0, then this, and if not, then this. But c is positive, then add 1 to it for a higher precision, and otherwise do not. For example, to divide by the amount 33 with 16 bits of precision, we compute n as this. 33, what should log 233 mean? We get 5, this would return 5. 5 minus 1, 4, we should get 20. And then we compute m as this. M is this because we got c, the number here, greater than 0, then we do not add. No, sorry, we do add 1 to it, and 2 power 20, god damn it, plus 1. So we have 2 power 20 divided by 33 is this, which is nearly equal to this, which is this in 16-bit, in hexadecimal. Therefore, multiplying a 16-bit number by 7C2016 and then shifting right 20 bits is equivalent to dividing by 33. That makes sense. Example 17. Division by constant 193. If I divide by a constant 193. To divide by a constant 193 with 32 bits of precision, the multiplier is computed using the equations above. We get m this way, m is this in 16 bits, and the shift amount is 38 bits. That is a crazy shifting amount. AArch64 code for division by a constant 193. Yo, we get the address. The following code will calculate W2 divided by 193. W2 signed multiply L. What does L mean? Arithmetic right, shift right, and subtract. But what is signed multiply large? I want the result to be in 32-bit, 64-bit result I want. And then example 17 shows how to calculate m and n for division by 193 on AArch64 processor. Division by a constant can be performed very efficiently. Listing 7.5 shows how division by 193 can be implemented using only a few lines of code. In the listing, the numbers are 32 bits in length, so the constant m is much larger than in the example that was multiplied by hand, but otherwise the method is same. Example 17 shows how to calculate m and n for division by 193. On AArch64 processor, a division by a constant can be performed very efficiently. Listing 7.5 shows how division by 193 can be implemented using only a few lines of code. In the listing, the numbers are 32 bits in length, so the constant m is much larger in the example that was multiplied by hand, but otherwise the method is used is the same. Here we have m, and that is this, and we put this into the third register like this. Okay, we have to use LDR when we are providing an immediate value from the lateral pool. We do LDR load. Note that there are only 12 non-zero bits, 12 non-zero bits, and the pattern this appears 3 times in the 32-bit number. The multiply can be implemented as, so we can make this efficient even more. So the following code sequence can be used on processors that do not have the multipliance instruction. Sign extend W this into this. and then move that into the zeroth register. Sin X and W. Yo, and this this is for dividing. Okay. This is a very optimal way for dividing. Okay, when we know exactly what we want to divide and how we want to divide. 150. God damn it, this is just so long. This 700 line C code. I think we can complete this today. Yeah, probably I guess. Okay, let's not waste time. Okay, division this. Let's consider this as we get some idea how division is done. We even wrote a program for division, and now we have some idea about how binary division is done. And my experience with the binary is that I do not understand it the first time I read it, and if I read it over a period of time again and again from different sources, that is, then it may starts making some sense instead of reading the same paragraphs again and again. If I am not understanding something, I can move on and read the explanation for the topic from some other source at some other time, and that explains things, right? Getting different perspectives, that is, touching the elephant from different points and trying to make sense. Dividing large numbers. Section 7.2.5 showed how large numbers can be multiplied by breaking them into smaller numbers and using a series of multiplication operations. There is no similar method for synchronizing a large division operation with a arbitrary number of digits in the dividend and divisor. However, there is a method for dividing a large dividend by a divisor given that the division operation can operate on numbers with at least the same number of digits as in the divisor. As in the divisor. Okay, that makes sense. Suppose we wish to perform a division of an arbitrarily large dividend by bit divisor, one digit divisor, using a basic division operation that can divide a two-digit dividend by a one-digit divisor. So the number of digits are double in the dividend compared to the divisor. The operation can be performed in multiple steps as follows. Divide the most significant digit of the dividend by the divisor. Divide, okay, just divide it. The result is the most significant digit of the quotient, okay. Prepend the remainder from the previous division step to the next digit of the dividend, forming a two-digit number, and divide that by the divisor. This procedure this produces the next digit of the result. Repeat 2 to form until all digits of the dividend have been processed. Take the final remainder as the modulus. The following example shows how to divide this by 7, only two digits at a time, by only using two digits at a time. Okay, 0 is the most significant bit in the quotient. Then I prepend 6 to the next digit and I divide, and 8 is the next MSB, and 5 I prepend 5 to the next number and I get this. And okay, that makes sense. This method can be applied in any base and with any number of digits. The only restriction is that the basic division operation must be capable of dividing a 2n-digit dividend by an n-digit divisor and producing a 2n-digit quotient and an n-digit remainder. That makes sense. For example, the AArch64 processor is capable of dividing a 64-bit dividend by a 64-bit divisor, producing a 64-bit quotient. The remainder can be calculated by multiplying the quotient by the divisor and subtracting the product from the dividend. Using this division operation, it is possible to divide an arbitrarily large dividend by a 32-bit divisor. By a 32-bit divisor. Uh, that makes sense because I can do 64-bit divisions, right? Yep. We have seen that given a divide operation capable of dividing an n-digit dividend by an n-digit divisor, it is possible to provide a dividend with any number of digits by a divisor. It is possible to divide a dividend with any number of digits by a divisor with n by 2 digits. Yes, unfortunately, there is no similar method to deal with an arbitrarily large divisor or to divide an arbitrarily large dividend by a divisor with more than n by 2 digits. In those cases, the division must be performed using a general division algorithm as shown previously. Okay. Now we move on to big integer, and now we know how division in binary case is done. That is cool, cool, cool. And now for big integer ADT, abstract data type, and what is the time and stuff. Well, let me just take a break, and I will be right back with my water. Yep, I'm back. And yeah, let's move on. Move on. Did you move on? Yes, big int abstract data type. For some programming tasks, it is helpful. It may be helpful to deal with arbitrarily large integers, for example, the factorial function and Ackermann, Mikasa Ackermann, and Levi Ackermann. Uh, it is Ackermann. Yep, it is Ackermann. Ackermann functions grow very quickly and will overflow a 32-bit integer for even small input values. Even a 64-bit integer is insufficient for holding the result of these functions with even relatively small inputs. The GNU C compiler is able to do some big number arithmetic using unsigned integer 128t, but even a 128-bit integer is insufficient for these functions. In this section, we will examine an abstract data type which provides basic operations for arbitrarily large input values. Listing 7.7, this goddammit, shows the C header for this ADT. Okay, and listing 7.8 shows the C implementation. Okay, and listing 7.9 shows a small program that runs a regression tests on the big integer ADT. A regression test is a relatively small test that is used to verify that changes to the code have not introduced bugs. Regression tests are very valuable tools in software engineering and are typically used in large companies by code testing specialists. Okay, so this is the header file, listing 7.7. The header file is 60 lines long, and here is the implementation, which is starting from here. We have the implementation for the above header file, which is one page, two page, three page, four pages, five, six, seven, 8, 9, 10, 11, 12, 13, 14, and 15 pages long. 700 lines long. Crazy. And this is a small regression test algorithm program that does uses the above thing. And okay, we do not have to understand all of this. Our main goal here is assembly and understanding things. So let us understand a little bit about what are regression algorithms, right? We can do that. And the thing is that this abstract data type, this 700 line code, this abstract data type provides us a way to store large numbers. It takes away the complexity for ourselves like abstract data types do, and it provides some interface through which we can manipulate very large numbers, and we do not have to think about how they are being manipulated. That is the whole point of having abstract data types. That is why we should not, it is not necessary to understand all of this, how it is being handled, right? And this program is using that this abstract data type to do some regression testing. I do not understand what is regression testing. So I will understand that. And these are the ways, the interface that it provides, that the abstract data type provides to work with big integers. and here it is working with them. Let's see what is regression testing. Regression testing is a type of software testing that ensures that recent code changes have not negatively affected existing functionality. It involves rerunning test cases that previously passed to verify that updates, bug fixes, bug fixes, and enhancements haven't introduced new defects. Okay, key points about regression, linear regression in machine learning. Key points about regression testing. Purpose: to confirm that new code changes do not break existing functionality. Okay, when to perform: after bug fixes, code refactoring, that is changing the code without changing the interface, enhancement, making new features, feature addition. Enhancement is maybe improving something. How it's done: by re-executing previously written test cases either manually or using automation. Okay. Automation, often automated using tools like Selenium, Jest, JUnit, Cypress. Cypress, what is the capital of Cyprus? Nicosia, to save time and improve efficiency. Scope can range from testing a small module to entire application depending on the changes. Type of regression testing. Unit regression focuses only on specific module or component where changes were made. Partial regression tests the changed module along with the related module to ensure compatibility. Complete regression runs all tests for the entire application. Would you like a more detailed explanation for automation? Okay, so regression testing only means that, wait, so regression test just is just a piece, not price, piece of software which keeps records of the tests which have been passed by the by a program, and uh, when some change is made to the uh, program, then we can run the regression test and test which in turn which then runs those previously passed tests on the program under question and checks if the tests are being passed even after the changes made to the program. Is that correct? Question mark. Yes, that is exactly right. A regression test is essentially a collection of previously passed test cases that are rerun under changes are made to after changes are made to a program. The purpose is to verify that the modifications haven't broken existing functionality. To break it down, initial test execution before any changes, the program is tested and passed. Passing tests are recorded. Code changes. A developer modifies the code. Example, adds a feature, fixes a bug, or refactors code. Regression test execution. The previously passed tests are executed again to check if they still pass. Results analysis. If all tests pass, the change is safe. If some tests fail, the change has introduced a bug, a regression that needs fixing. What does regression in general term mean? Sorry, my bad. In general term, regression means moving backward or returning to a previous state, often implying a decline or deterioration. Okay, well, starting from nothing, got at some place and then regressed back to nothing. Common uses of regression. General meaning to go back to an earlier condition, often a worse one. Example, after making progress in his recovery, he suddenly regressed and had to return to therapy. Psychology, returning to an earlier mental or behavioral stage behavioral behavioral stage, often due to stress or trauma. Example, under pressure some people regress to childish behaviors. Okay. Mathematical statistics in regression, George Hotz. In regression analysis, it refers to identifying relationships between variables. A regression model predicts how one variable depends on another. Software development, regression testing. The latest update caused a regression in the login feature. Okay, okay, we get it. Now, the implementation could be made more efficient by writing some of the functions in assembly language. One opportunity for improving is in the add function, which must calculate the carry from one chunk of bits to the next. In assembly, the programmer has direct access to the carry bit, so uh, carry propagation should be much faster. When attempting to speed up a C program by converting selected parts of it to assembly language, it is important to first determine where the most significant gains can be made. Profilers such as gprof and callgrind can be used to help identify the sections of code that will have the greatest impact on performance. It is also important to make sure that the result is not just highly optimized C code. If the code cannot benefit from some features offered by assembly, then it may not be worth the effort of rewriting in assembly. The code should be rewritten from a pure assembly language viewpoint. Okay, the code should not be highly optimized C code. If we are writing some part of the C program in assembly, then we have to write it with the viewpoint of assembly, pure assembly viewpoint. And this line. A profiler such as gprof and callgrind can be used to help identify the sections of the code that will have the greatest impact on performance. What does gprof does? Ah, gprof does. Gprof is a performance analysis tool used to identify hotspots in a program by profiling execution, essentially showing which features are taking the most CPU time and how they call each other within the call graph, helping developers optimize the most impactful parts of their code. It works by instrumenting the code during compilation, and it only works for compiled code, okay, and then analyzing the collected data during program execution to generate a detailed profile. That makes sense. It tells us which parts of the code are taking the most amount of CPU usage. And yeah, it is also important to avoid premature assembly programming. Make sure that C algorithms and data structures are efficient before moving to assembly. If a better algorithm can give better performance, then assembly may not be required at all. Once the assembly is written, it is more difficult to make major changes to the data structure and algorithms. Assembly language optimization is the final step in optimization, not the first. Makes sense? Well-written C code is modularized with many small functions. This helps readability, promotes code reuse, and may allow the compiler to better optimization. However, each function call has some associated overhead. If optimal performance is the goal, then calling many small functions should be avoided. For instance, if the piece of code to be optimized is in a loop body, then it may be best to write the entire loop in assembly rather than writing a function and calling it each time through the loop. Makes sense? Writing in assembly is not a guarantee of performance. Spaghetti code is slow. Spaghetti code when you are changing the program counter from one memory location to the next, and it just keeps moving over all over the place, and you have a spaghetti if you plot the graph. Load store instructions are slow. Multiplication and division are slow. The secret to good performance is avoiding things that are slow. Good optimization requires rethinking the code to take advantage of assembly language. Okay, the profiler indicated begint etc is used more than any other function. If the assembly language can make this function run faster, then it should have a profound effect on the program. We will leave that as an exercise for the student, but we'll give an example of how to optimize a less critical function. So is that an exercise? Multiply this by this. Demonstrate the division algorithm used in section this. Exercise chapter 5. Modify our program for this. Shit. But we got this. We got this. In the end, these three questions want us to write an optimized versions of a few functions which are used in this behemoth. In this behemoth, we have to rewrite those functions in assembly with some optimization. Okay, we got this. We got this. Now, the profiler indicated that begin to see and for the student, but we'll give an example of how to optimize a less critical function. Big int and negate function was rewritten in assembly as shown in listing 7.10. Note that the original C implementation used the big int complement function to get the first one's complement and then used the big int ADC function to add one. The C implementation of the BigInt ADC function requires extra code to calculate the carry from one chunk to the next. Okay, however, the assembly version of BigInt complement loads each chunk, complements it, and propagates the carry all in one step. That makes sense because we have add C command in assembly. Since it only loads and stores the data once, and instead of twice and requires much less work to propagate the carry bit, we will expect the assembly version to run about twice as fast as the C version. And here is the assembly version. God damn it. It is just too goddamn big. 32-bit and 64-bit version CCC, and here are the times. In C, this took this, and this took this, and this sped up was 1.96 twice. Program the whole pro oh, it also affected the whole program only a little bit. Now the regression testing program was executed on an NVIDIA Jetson TX1 using the C version of Big Int Negate, and then with the assembly version this was done for chunk size of 32 bits and 64 bits. The results are shown in the above table. The total time required for the negate function tests using The 32-bit C version was this second, and for this is this uh, version was this much, and sped up for sped up for 1.96. Okay, so writing that function in assembly did help quite a bit. It made our code run faster twice. The big int negate function also has a small impact on the functions that rely on it, so the overall time to run the regression tests was also reduced slightly. Yep. The 64-bit assembly version was 5% faster overall than the 32-bit C version because this function was not called often in the test program. The overall program speed was modest. Implementing other functions such as big int add and big int sub in assembly would result in much larger overall speedups. And we can do that. We can do that. Of course, we can do that. 7.5 chapter summary. Complement mathematics provides a method for performing all basic operations using only the complement, add, and shift operations. Addition and subtraction are fast, but multiplication and division are relatively slow. In particular, division should be avoided whenever possible. The exception to this rule is division by a power of the radix, which can be implemented as a shift. Good assembly programmers replace division by a constant c with multiplication of the reciprocal of c. They also replace the multiply instruction with a series of shifts and add or subtract operations when it makes sense to do so. These optimizations can make a big difference in performance. That also makes sense. Writing sections of a program in assembly can result in better performance, but it is not guaranteed. The chance of achieving significant performance improvement is increased if the following rules are used. Here are the rules. Only optimize the parts that really matter. Yep. Design data structures with assembly in mind. Yep. Use efficient algorithms and data structures. Okay. Write the assembly code last. Yep. Ignore the C version and write good, clean assembly. Yep. And reduce function calls whenever it makes sense. Yep. Because we do not want spaghetti code. Avoid unnecessary memory access. Memory access is slow. That is the reason. Write good code. The compiler will beat poor assembly every time, but good assembly will beat the compiler every time. Yep. Understanding the basic mathematical operations can enhance the assembly programmer to work with integers of any arbitrary size with efficiency that cannot be matched by a C compiler. However, it is best to focus the assembly programming on areas where the greatest gains can be made by using a profiler. And then tomorrow we will have to do these exercises. What are these? Multiply minus 90 by 105 using 8-bit binary division to form a 16 signed 16-bit number. Show all of your work. Show all of your work. Okay, I will be streaming so you can see all of my work. Then multiply this and this using unsigned 8-bit multiplication to form an unsigned 16-bit number. Okay, write a section of AArch64 assembly to multiply the value 1 by 13. 13 is binary number using only shift and add operations. Okay, these first parts will be the following code will multiply the value in 0 by a constant c. What is the constant c? By a constant c. What is the constant c? Okay, the value is in the 0th register that we are multiplying, right? So first we add to itself its left shifted value, that is we multiply it by 3, and that multiplied by 3 version is here, and to that multiplied by 3 version we add the original value multiplied by 4. So 3 plus 4 7. The answer should be 7 for this. Then we have other questions, I guess. Yeah, we got this. Tomorrow we will only do these 13, well, not like only, but at least these 13 questions, and that Should be good. And this is enough for today.